This is the notebook for the video, Entropy in Physics and Information Theory. We will use a toy model to illustrate the difference between entropy in these two fields. We will skip the function definitions of the toy model and focus on examining the difference. We will create a chamber having 4 rows with 4 cells in each row. The initial state is a snapshot where 100 molecules are injected into the chamber and are all concentrated in the top right cell. We will calculate the entropy for this state, from both physics and information theory perspective. It is a single number in both cases. The entropy is lower in physics, compared to information theory, for this state. Now we will disperse the molecules into other cells of the chamber to simulate diffusion. We will calculate the entropies again for a snapshot of the dispersed state. Now the entropy is higher in physics compared to information theory. This simple toy model shows that entropy is not the same in physics and information theory. Entropy quantifies different things in these two fields. In information theory, entropy of an event captures the surprise value of an event. Low probability events have high surprise value and high probability events have low surprise value. We use a hypothetical simple distribution to capture this in the toy model. That is, we assign a low probability, or high surprise value, to the initial state where all molecules are in a single cell of the chamber. And we assign a high probability or low surprise value for all other dispersed states of the molecules. This assignment of probability may look contrived, which it clearly is. But it captures what entropy in information theory means. In physics, entropy is not a measure of surprise. It is a measure of the number of arrangements a system can have. More the arrangements, higher the entropy. In our toy model, the entropy calculation function for physics assigns a probability value for each cell, simply by dividing the number of molecules in a cell by the total count of molecules in the chamber. So, in the initial state, where all molecules are in a single cell, the probability of finding a molecule in that cell is 1, and 0 in all other cells of the chamber. As the molecules disperse, they are spread across the cells in the chamber. Most cells have non-zero probability of having molecules now, and this increases the entropy. If we examine the formula for computing entropy in information theory and physics, we see that both the entropy formulas have the same mathematical form, other than the logarithm base and the constant. They are both sums of the negative logarithm of the probability of an event, weighted by the probability of that event. Yet we get completely different answers. When one is high in a state, the other is low, and vice versa. The reason is the difference in what the probabilities are capturing in these fields. In the case of physics, the probabilities reflect the likelihood of the system being in a particular configuration. In contrast to physics, in information theory, the probabilities represent the likelihood of observing a specific event from a set of possible events. A few caveats about this toy model. When computing entropy for information theory, we are assigning probabilities to specific snapshots of the system, rather than the dynamic behavior of the molecules over time. Also, as mentioned earlier, the assignment of probabilities is contrived to illustrate the difference. We are also oversimplifying when we said the mathematical form of entropy in the two fields is the same. While there is a similarity in the structure of the formulas, both involve summing over probabilities. The interpretation and the way probabilities are determined are very different. For instance, in many physical systems, entropy calculations don't necessarily involve probabilities directly. Instead, they might involve counting microstates or other methods, particularly in more advanced contexts.